All right, so welcome to tonight's live session. I am covering how to factor out the greatest common factor. So I have several examples for you that I will go through, of course. So if I can get my screen to cooperate and actually go to the next slide. There we go. Okay, so the greatest common factor is abbreviated GCF. So in order to understand what this is, we need to actually break down the terms. Let's start with the word factor. So a factor is a number or quantity that when multiplied with another produces a given number or expression. So this makes much more sense if you see examples of it. So 2 times 3 equals 6. That is something that we know. So 2 and 3 are factors of 6. Because those numbers multiply to 6. 6 has lots of factors. So any number that can divide into 6 can be considered a factor. So your factors of 6 are 1, 2, 3, and 6, because 1 times 6 is 6 and 2 times 3 is 6. So you can think of a factor as something that you multiply by something else, or you can think of it as something that divides evenly into something else. The greatest common factor. So common means we have to look at factors in more than one item to look at what they have in common. And then greatest means the largest one they have in common. So the greatest common factor, 2 or more integers, which are numbers, is the largest factor common to each integer. So let's say I take the factors of 8. So I'm listing all the numbers that divide into 8. That's 1, 2, 4, and 8. So the greatest common factor is the biggest number they have in common, which is 2. So the greatest common factor between 6 and 8 is 2. So you can find the greatest common factor by writing down all of the factors, or you can use prime factorization. I use prime factorization if it's not something I can figure out mentally, or if they are really large numbers. So for 6 and 8, I can figure that out mentally. I know 2 is the biggest number that I can divide into both of those. That's how I think about it. But if it's something larger, like let's say I was looking at 56 and 120, I'm going to make a factor tree. I'm going to do prime factorization because that's not something I can do in my head. So here's an example. This one I could do in my head, but I can also do a factor tree. So we want to find the greatest common factor. So we got 30 and 42. So we're looking for the biggest number I can divide evenly into both, which would be 6. 6 goes into 30, 6 goes into 42. And that is, as far as I know, off the top of my head, the largest that goes into both. But I can also do a factor tree. So I'm going to do the factor tree. I'm going to do the prime factorization of 30. So 30 can be split into 6 times 5. And 5 is a prime number, so I'm going to circle that. And then 6 can be split into 2 times 3, and those are both prime numbers. So the prime factorization of 30 is 2 times 3 times 5. 42 is 6 times 7. So 7's prime, and then 6 is 2 times 3. So you can see by the way I split this up that we have 6 times 5 and 6 times 7. So the largest number they have in common is 6. But the other way to figure that out is by highlighting, or basically taking a look to see what factors they have in common. So they both have a 2, and they both have a 3. Those are the only things they have in common. So if you multiply those together, your greatest common factor is 2 times 3, which is 6. So that's how it works if you do a factor tree. You look at what's in common, and then you multiply those all together. Here's the second example, and here we have 3 things in common: 28, 63, and 7. Off the top of my head, well, the largest number that divides into 7 is 7, and I know that 7 divides into 28 and 63, so I know the greatest common factor is going to be 7. But let's go through the prime factorization to demonstrate that. So 28 is 7 times 4. 7 is a prime number. And then 4 is 2 times 2. 63 is 9 times, I'm using my finger trick, 9 times, wait, 63. 7th finger down, 9 times 7. 7's prime, and 9 is 3 times 3. And then 7 is just 7 times 1, if you really want to make that a factor tree. So the only thing they have in common is 7. That's the only factor in common, so that means the greatest common factor is 7. So now let's take a look at variables. So you may be familiar with the greatest common factor with numbers because you're looking at that when you're trying to reduce fractions. When you're trying to reduce a fraction, you want to divide out the biggest number because that saves you steps. When you have variables involved, you don't think that it's going to be more complicated. It's actually easier than if you have numbers. So when you have an expression that has variables, or more than one expression that has variables, your greatest common factor is the variable with the smallest exponent. So in green or teal here, the greatest common factor out of x to the third and x to the fifth is x to the third because that's the smallest exponent. So you just match up your variables and then you take the one with the smallest exponent. When binomial expressions are involved, then you also look at the smallest exponent. So that's the one in blue, the GCF of x plus 3 and x plus 3 squared is x plus 3. Because the exponent in x plus 3 is a 1, you can't really see that, let me switch my color, is a 1, and 1 is a smaller exponent than 2, so you take the one that has the exponent of 1. So with variables, you don't even need to do prime factorization. You basically don't have to do any thinking. You just look which has the smallest exponent, bam. So it's actually easier than with numbers. So I've got 3 separate examples here on this slide where we want to find the GCF. So first, 3xy and 7y. So 3 and 7 don't have any numbers in common because they're both prime. So if your numbers are all prime and they don't have anything in common, your GCF is going to be a 1. And then you add on your variables. So 3xy has an x, 7y does not. So that means they don't have an x in common, so I can't take that out, I can't factor that out, I can't divide it out. So x is not included in the GCF. They both have a y. The exponents on the y are the same, they both just have a single y. So that means my GCF is 1y. That's what they have in common. Now, the second example here, I have 12w cubed z and 16w squared z. So we want the greatest common factor out of 12 and 16. So I'm going to just make factor trees here, even though I can do these mentally. 12 is 4 times 3, 4 is 2 times 2, 16 is 4 times 4, and 4 is 2 times 2. So I can split each of those up. And then if I highlight what's in common, they both have 2 times 2 in common, but that's the only thing that matches, and 2 times 2 is 4. So I can write my GCF as 2 times 2. And then let's look at the w. So I have a w cubed and a w squared. So I take the smallest exponent, which would be 2. And then I have a z and a z. So those are the same, so I have a z. So my GCF will be 4w squared z. Oh, my battery is getting low. Let me plug myself in. Yeah, it's having issues. It doesn't want to go in the slot. I don't know why. It's magnetic. You'd think that it would be... There it goes. Okay. third one here, 15 r squared s squared t to the fifth and 5 r cubed s to the fourth t cubed. So with the 15 and the 5, I will, even though I can do these in my head, I'm just going to make these factor trees. So 15 is 3 times 5, which are both prime. 5 is 5 times 1. So the only prime they have in common is 5. So that's going to be the numerical GCF, the number I can take out of those. And then I look at my r's. One has an exponent 2, one has an exponent of 3. The exponent 2 is smaller, so I'm going to have an r squared. Then I look at my s, exponent 2, exponent of 4, so I'm going to take the 2 because that's smaller. And then the t's, I have an exponent of 5 and an exponent of 3. 3 is smaller, so it's going to be t cubed. So your GCF is 5 r squared s squared t cubed. So you can see with the variables that you don't even really need to do any thinking other than which number is smaller, which exponent is smaller. The hard part is the number part to find the GCF. So the whole reason we need to figure out what the greatest common factor is so that we can factor that out. And so factoring means reversing the distributive property and multiplication of polynomials. So when we have the distributive property, let's say I have 2x times x squared plus 5. So each of these are factors. And so when we multiply that out, we get 2x cubed plus 10x. So when we are factoring, we find the greatest common factor. We factor it out. That basically will take us back to where we started, as long as you have the GCF in front. So we're going to factor it out so that we're turning into things multiplied together. And the reason why we do this is because when we work with polynomials, which is something that you've heard that term last week about polynomials, and we're multiplying polynomials. When we start solving things that involve polynomials, they need to be in the form where you multiply. And when you go to college algebra and you have to start simplifying rational expressions that are fractions with polynomials, in order to simplify, you need to factor. So factoring is used a lot going forward. So being able to do this is really important. So to factor things out, there are two different methods. Method 1, this is the book method. This is what the book tells you to do. And I actually don't use that method. So method 2, we're going to call the SK method. So method 1 is to, both methods actually, first you have to figure out what the GCF is. Then step 2 is to rewrite what you have, but the way you rewrite it is different. So in method 1, you rewrite each term as things multiplied together, the GCF and what it's multiplied by. In my method, I rewrite it so your GCF is in front and then you're dividing each term by the GCF. So one, you're writing it as multiplication, one, you have division. I do the division method because I think it's easier for people to do that, because then all you have to do is follow the rules of exponents where you subtract your exponents. If you do the multiplication method, you have to think about what times what gets me what I want, and it's a little harder. I can do it now that I've done math forever, but if you're not that great at math, it's a little harder because it's a little more thinking involved. For method 1, use the distributive property to remove the greatest common factor. So you're reversing the distributive property, and that's not usually obvious to people. In my method, you just have to follow the rules of exponents. So I think my method is easier. I'm going to show both methods so you can see the comparison. So this example, we want to factor the greatest common factor out of 3q minus 15. So I'm going to find the GCF separate from my boxes here. So when we're finding the GCF, we are looking at 3q and negative 15. So that's how we separate it out. And so the GCF, I'm going to look at the number first. I'm looking for the biggest number I can divide into 3 and 15, which is 3. 3 goes into 3, 3 goes into 15. So if I made my little factor trees here, and if I ignored the negative sign with the 15, I would have 3 times 1 and 3 times 15. So 3 is in common. And then 1 has a q, 1 doesn't. So to not have a q is what you have, because the exponent, if you thought about it, the exponent on the 15 would be q to the 0. So because there's nothing there, and so that's what you would take, which means there's no q basically, because there's not a q in common. So our greatest common factor here is just 3. So what method 1 means is that you start with 3q minus 15, and then you rewrite it so that it's that 3, the greatest common factor, is clear. So you can rewrite it as 3 times q with parentheses minus, and then 3 times 5, because that gets you 15. So the GCF is written in both of them, and then what you have to multiply by to get up to where you started. Then you are reversing the distributive property by putting that in front and then taking what's left over. So that's 3 in front and then q minus 5. That's undoing the distributive property. So if you showed the steps of the distributive property, this might look similar to what you had to do before, where you take what's in front, you multiply it through. So it's like we're working backwards from what you would normally do when you distribute. So that's method 1. And for this problem, method 1 is completely fine. That doesn't, it's not too hard. Method 2, my method, here's what I would do. So I have 3q minus 15. And then my next step is to put the GCF in front, and then to take each term and write it over the GCF. So I'm going to just highlight. I have my GCF in front, and then I'm dividing each one by the GCF. And then I simplify. 3 divided by 3 is 1, so I just have a q. 15 divided by 3 is 5. So you get the same answer, and it basically takes the same number of steps. It's just a matter of which one makes sense to you and the way that you think. For this particular problem, I would say maybe method 1 is better. But let's take a look at one where maybe it's not better. So this example. In this example, I actually prefer method 2. And I'll do it both ways, and we'll see which one you prefer. So we have 16d cubed plus 24d squared plus 32d. So I need to find my GCF. So let's just look at the numbers. I have 16, 24, and 32. So I'm going to do my factor trees. So 16 is 4 times 4. 4 is 2 times 2. 24 is 6 times 4. 6 is 2 times 3. Oops, I didn't mean to circle the 6. 4 is 2 times 2. And again, I circled the 4. I'm just getting circle happy here. And then 32 is 8 times 4. So looking at this, oh, I circled them again. I'm thinking, oh, 4 must be it. 8 is 4 times 2, and 4 is 2 times 2. So I'm kind of running out of room here. Okay, I'm going to highlight everything. So I've got a 2, a 2, and a 2. I still have another 2 in common. I've got a third 2 in common, and then I don't have another 2 in 24. So actually my GCF here is 2 times 2 times 2. So that's going to be 8. And so my GCF out of 16d cubed, 24d squared, So d cubed, 24d squared, and 32d is going to be 8. And then when I look at the exponents, the smallest exponent's on the d, so the GCF is 8d. So now that I've determined the GCF, now we need to use the methods to factor. So method 1, so I'm going to start. We've got 16d cubed plus 24d squared plus 32d. And so each of these, I'm going to start with my GCF. And now I have to fill in the blank. So 8 times what gets me 16? So 8 times 2 is 16. And then d times what gets me d cubed? Well, I need 2 more d's, so that's d squared. And then I have my 8d. I should have made my table a little wider here. I'm running out of room. 24, so 8 times 3 is 24. And then I need a second d to get to d squared. And then 8d. And then to get to 32, 8 times 4 is 32. So you have to do a little thinking there and think, okay, 8 times what will get me to the other parts, and then you have to look to see what's left over for the variable. Now, what you do is you put that 8d in front, and we're reversing the distributive property, so that leaves us 2d squared plus 3d plus 4. Basically, everything that was not the GCF gets put in parentheses. And so your result is 8d times 2d squared plus 3d plus 4. So I think the hardest part on this method is step 2, where you're trying to rewrite it. So now let's take a look at my method. So I start, I'm going to do this in different colors, so because I know I'm going to be running out of room here. I have 16d cubed plus 24d squared plus 32d. So my method says I start by writing out, I'm actually going to skip a line so that it doesn't, I have more room. So I start with my GCF in front, and then I take each of these and I write it as a fraction over the GCF. And then my next step is to divide. 16 divided by 8 is 2. I subtract the exponents. 3 minus 1 is 2, so that's a 2d squared. 24 divided by 8 is 3. Subtract exponents. 2 minus 1 is 1, so I have just a 3d. And then 32 divided by 8 is 4, and a d over d cancels. So we get the same exact answer. But for me, I find the second way is easier in this case because it's a lot easier for me to do this division because I'm just doing the division and then subtracting exponents. For some, it's the same thing essentially. It's just another way of thinking about it. The first way, method 1, I find that it's harder for me. I have to do more thinking there because I have to do the division sort of and then write what the result is. It's like I'm doing the division at the same time. It's just harder for me. But both methods work. So use whichever method works for you. So now I'm going to move to example 6, and I'm actually going to use both methods here. I'm going to use method 2 for the first one and method 1 for the second one. So I'm going to put this back into black. I'm going to use method 2 and then method 1. And that is because the second example here is easier to use method 1 in because it's already done for you basically. It's already set up. So actually let's do that one first. I should have put that one first. So if you notice, the second example here is 7 and then in parentheses x squared plus 1, then minus y times x squared minus, or x squared plus 1. We have two things in common. So that is our GCF. That's like the second line here, where whatever is the same in all the terms is your GCF. So our GCF, the greatest common factor, is x squared plus 1. So to factor it, we put that in front, and I have to have the parentheses because it contains more than one thing. And then what's left over? 7 minus y. So this is using method 1, where we're reversing the distributive property. We just didn't have to figure out the GCF because it was done for us. What we just did here is generally called grouping, or it's part of the grouping process. It's not the whole grouping process, but it's the pattern you get when you use grouping. And then this is also used when we use the AC method. So those are things that I will get to in later sessions. But anything that involves grouping or the AC method, you'll end up having something that looks like what we started with here, where you have in parentheses something that matches. And then you pull it out, and then you write what's left over. So that is used for grouping and the AC method when we factor. Okay, so now going to the first example here where I'm going to use method 2. And method 2 I use if I'm not grouping or if I'm not using the AC method. And method 2 is good to know because that is useful if you have to go on to pre-calculus or calculus. So there is a place for both of these methods. That's why I don't think you should just learn the one method that the book teaches you. It's good to learn both methods. So first we need to identify the greatest common factor. So I'm going to first do my factor trees. So 9 is 3 times 3. 3 is 3 times 1. 12 is 4 times 3. And then 4 is 2 times 2. So they have a single 3 in common, and that's the only thing they all match with. So the GCF is going to be 3. And whenever your first thing is negative, the leading term is negative, your GCF is negative. And this is just a rule that will make things easier going forward. So we don't have to do it this way, but because it makes the rest of everything we do easier, that's the standard. So it's negative because I have a negative in front, and then a 3 because that's what I have in common. And then when I look at the y's, I have a 5, a 3, and then the exponent, and the last one is a 1. So 1 is the smallest, so it's going to be minus 3y. So now the way method 2 works is I write that GCF in front, and then I divide each term by the GCF. And I'll separate them out with plus signs and then include the negative sign whenever you're dividing by a negative, because that will just help you see that you have a negative and a negative, which makes it positive. So I have a negative 3y in front, and then a negative 9 divided by negative 3 is a positive 3. And then when you subtract exponents, 5 minus 1 is 4, so that's y to the 4th. 3 divided by negative 3 is negative 1. I subtract the exponents, 3 minus 1 is 2. Negative 12 divided by negative 3 is 4. Y over y, that cancels. So we get negative 3y times 3y to the 4th plus negative y squared, or you could say minus y squared, plus 4. Why did my box just disappear? That was weird. It disappeared again. Okay. It really doesn't want me to box that. So that is factoring out the GCF. The key is identifying the GCF and then picking whichever method works for you in your brain. When I do the next factoring, which is tomorrow at 11 a.m., I'm going to go over factoring trinomials. And so that is going to be doing trial and error, guessing and checking. So I will not be, there will be some factoring of the GCF out first and then doing guessing and checking. The session on Monday, which is using the AC method, that's where I will start going back to grouping and doing that method 1 that I mentioned. So that is it. Oops, I don't know why the screen just went blank. I probably accidentally hit something. There we go. So if you have any questions, you are welcome to email me. You can give me a call, send me a hangout. I'm going to try to get this posted at least on YouTube tonight, probably in the classroom tomorrow. So I look forward to hearing from you guys and see you tomorrow at 11 a.m. Alrighty, bye.